All right, Math 3. Welcome to Unit 6, Lesson 3. This is again review material. Earlier in the unit we kind of covered graphing, and today we're going to cover solving and evaluating. So let's take a look. Go ahead and try the worksheet on your own. You should be able to do most of them, and then refer to the video that I'm making to check your answers and to fill in any gaps that you've forgotten. So I'll go ahead and get started. Our first equation, you can see this is linear, has a slope of -4, a y-intercept of 5, and they're asking us to put in an input of 3, or in other words, an x value of 3. So, piece of cake, simply insert 3 into your equation. -4 times 3 is -12. And -12 plus 5 is -7. So a of 3 gives us -7. In other words, an input of 3 for x will give an output of -7 for y. So you could also, again, think of that as an ordered pair or a point on the graph of that line. Okay, letter B. This time, they're asking what input will give me an output of, in this case, 17. So here, I'm going to say output is 17. And I'm going to solve for the unknown input. So subtracting 5, I find that the input must be -3. And again, you can think of that as an ordered pair. When x is -3, y is 17, or an input of -3 yields an output of 17. Okay, moving on. Our next section is dealing with quadratics. Okay, our first question, we're going to ask, when does this quadratic have a 0, right, or a root? So we simply set the quadratic equal to 0. Now we have 4 choices on how to solve this. We could try graphing. I would only choose graphing if I have Desmos handy. And even then, if it's an irrational answer or a complex answer, Desmos is not the best choice. So typically, my go-to is going to be factoring. Factoring is quick. It's perfectly accurate. The downside is not everything will factor nicely. In this case, though, I am noticing that it will factor nicely, because 2 times -4 would give me -8, and then if I add 1, I could get my -7. So I'm going to factor this. Okay, so to get my 2x squared, I know I'm going to have 2x times x. To get my -4, I'm going to choose -4 and +1. But I want the -4 to be over here, because then I get the 2x times -4 giving me the -8. I put the +1 here, giving me +1x. So -8x plus 1x will give me my -7x that I need. And now it's factored. And since it's equal to 0, the zero product property tells me that one of these factors must be equal to 0. So I can say 2x plus 1 could be that that factor is 0, in which case we would get -1/2. Okay. Or my other factor, x minus 4, could be 0, in which case I get 4. So there are my 2 zeros or roots or intercepts for my parabola. Okay, moving on. Same thing, just another quadratic equation equal to 0. Okay. Now this time I'm, again, trying factoring first, because that's kind of my preferred method. 14, I could do -1 times -14, but that'll give me -15 as my middle term. I could do negative 2 times negative 7, but that would give me negative 9 for my middle term. So I can see this is not going to factor. So I'm going to have to choose one of the other methods. And since it doesn't factor, Desmos would not be a good choice because I'm going to get irrational or complex roots, which Desmos can't really give me accurately. At least not perfectly accurately. So my other two choices would be quadratic formula or completing the square. And of course, quadratic formula comes from completing the square. But you can go with either of those two methods. How about we do quadratic formula? So remember, this is A is 1, B is negative 6, C is 14. So I would say x equals negative b. So in this case, that becomes 6 plus or minus the square root of b squared. So that's going to give me 36 minus 4 times a, which is 1, times c, which is 14. All over 2 times a, which was 1. Okay, so working this out. Okay, and earlier on, when you first learned about quadratics, you would say, whoa, wait, this is going to be square root of a negative, and you were lucky you could just stop there and say no real solution or no real roots, which is still the case. There are no real roots here, but there are 2 complex roots, and we now know how to deal with those. So let's go ahead and continue with the problem and find our complex roots. Okay, square root of negative 20 will simplify. So that's going to be 2i radical 5. And both factors can divide by 2, so I can go ahead and simplify that. So 3 plus or minus I radical 5. There's my 2 roots, complex conjugates, and again, you could see Desmos would not be able to find those for us. All right, moving on. We're going to still work with quadratics, but this time we're going to make them inequalities. So take our quadratic equation, and we're going to say, when is it greater than or equal to 5? Okay. I would go ahead and get this equal to 0. So 2x squared minus 7x. I would have to subtract 5, so that would be negative 9. And I'm just going to say equals 0. Solve it like an equation at this point. And I'm going to check, could I factor this guy? And yes, indeed I can, because I'm seeing 9 minus 2, right? That would give me 7. So I'm going to go ahead and factor this guy. So a 2x and an x, that's going to give me my 2x squared. Okay. Now I don't want to put 9 over here because then it would be 9 times 2. That would give me 18. I want my 9 over here, and I want it to be negative. And then I want a positive 1 over here, right? Negative 9 times positive 1 will give me the negative 9. But from a middle term, right, I have a positive 2x here and a negative 9x there, right? Positive 2 minus 9 is negative 7. That's what I want. Okay. So solving, 2x minus 9 equal to 0 gives me 9 halves. X plus 1 equal to 0 gives me negative 1. There's my roots. Now, I have to go back. This was an inequality. I wasn't trying to find just the roots. I was trying to find all the values where this function is greater than or equal to 5. So think about the graph, right? I would have a parabola opening up because my a value is positive 2. And I know I have a root on the left at an x value of negative 1 and a root on the right at an x value of 9 halves, or 4.5. So the question is, would I be shading inside or outside of this parabola? And the quick way to figure that out is to test the value. So an easy value to test is 0. 0 is inside of my parabola. It's between negative 1 and 9 halves. So go back to my very original problem and plug in 0 for x. Okay, when I plug in 0 for x, I would get negative 4 is greater than or equal to 5. That's a false statement. So I know that 0, which is inside the parabola, is false. It's not a solution. That tells me it's everything outside of the parabola, right? It's everything out here, right? That would be where my solutions are. But you can confirm that by trying a value like negative 2 in the original. So plug in a negative 2. 2 times negative 2 squared, that's 8. Plus 14 is 22 minus 4. Well, 22 minus 4, that is greater than 5. So you can see a value like negative 2, which would be out here, works. And you can confirm again by choosing a value greater than 9/4. So a value like 5, for example. 2 times 5 squared is 50. Minus 35 is 15. 15 minus 4 is 11. And sure enough, 11 is greater than 5. So values over here also work. So I know that my solutions are outside of the parabola. In other words, they're below negative 1 for x and above 9/2 for x. So I could say anything from negative infinity to negative 1. Negative 1 is included, right? Union and included 9/2 to infinity. Okay, so there's my solution. All right, moving on. More of the same. We just have an inequality with quadratics. So just go ahead and set the quadratic less than 9. Okay. Subtract 9 and make it an equation. Find your roots. This factors. Okay, so my roots are at 5 and 1. So again, think of your parabola. The a is positive, so your parabola is opening up. I have a root at 1. I have a root at 5. Oh, I'm sorry, this should have been a dotted parabola. It's dotted because the boundary is not included. And now the question is, am I inside the parabola or outside the parabola to shade and find my solutions? So again, try 0 back in the original problem. I would get 14 is less than 9. Well, 0 is out here and it does not work. That means it's the values inside the parabola. And again, if you want to confirm, try a value like 2. 2 squared is 4. Minus 12 is negative 8. Plus 14, that would be 6. And yes, 6 is less than 9. So it's values inside my parabola that represent the solutions. So in other words, between 1 and 5. Okay, so there we are. Values between 1 and 5. Or if you prefer, I know some of my students would rather write their solution like that. That's fine too. Okay, moving on. Our next section deals with absolute value functions. Our first example, they want me to give an input of negative 2.5, so simply replace x with negative 2.5. Okay, and now evaluate. Okay. And here's where I get to take the absolute value. Once it's simplified inside the absolute value bars, that's when you do your absolute value operation. So this is going to become negative 2 times a positive 6.5, which is negative 13, and negative 13 plus 7 is negative 6. So there's our output for that function when our input was negative 2.5. All right, next we have an output for the absolute value, and we're saying, hey, what input or inputs would give me that output? So go ahead and set it up. Say 8 equals. the function. Okay. And now solving this, okay, so I subtracted 7. Now I'm going to divide by -2. And at this point, alarm bells should go off. I have an absolute value isolated. It's all by itself. And I'm saying, oh, take the absolute value of this quantity, and it needs to equal a negative value. Well, you should know the absolute value of any quantity can never equal a negative value. The lowest it can go is 0. Well, it can't go -1/2. So no x value will make this work. So this is a no solution. There's no such input that will work on this. Okay, moving on, absolute value inequality. So take my inequality, and when is that going to be greater than 1? Okay. Isolate my inequality. Isolate my absolute value. So subtracting 7. Some students will stop here and go, oh, hey, absolute value, negative, but we haven't isolated the absolute value yet. We still have to divide by -2. Make sure to reverse your inequality when you divide by a negative. Okay, now the absolute value is by itself, and I have a positive number here, so we don't have any alarm bells going off. We're just going to proceed in solving our problem. So what I want to find are my zeros, my roots, right? This is a V-shaped graph. I want to find those two intercepts. And then I ask myself, well, am I shading in between them or am I shading outside of them? So I'm just going to say, when is x minus 4 equal to 3? Well, when x is 7. Right? Then I'm going to say, well, when is x minus 4 equal to -3? Right? Because it could be that this was -3 in here and the absolute value turned it into +3. So there are my zeros. So I now have a V-shaped graph, and my zeros are at 1 and 7. Oh, I'm sorry, I did it again. This should be a dotted graph because the boundary is not included. Okay, so go back to your original problem and try a value like 0 and see if 0 works. If 0 works, it's outside of the V. If 0 doesn't work, then it's the values inside the V. So putting 0 in, that would give me -2 times 4, which would give me -8, plus 7 is still a negative value, and that is not greater than a positive value. So 0 didn't work. It must be values inside. But let's go ahead and confirm. So let's try a value like 2. Okay. 2 minus 4, that's -2. Absolute value of that is 2. -2 times 2 is -4 plus 7. Yes, indeed, that is greater than 1. So its values inside my V. So in other words, its values between 1 and 7. Okay, or we could again say x is between 1 and 7. Okay, moving on. Our next function type, step functions. So we've got a step function here that's a ceiling and a step function over here that's a floor. Our first question is, let's look at our ceiling function. Let's put in 2.5. So 2 and times 2.5. Okay. Now we have to evaluate the step function piece before multiplying. So we have to round 2.5 up. 2.5 rounds up to 3. So this is going to be 2 times 3, which is, of course, 6. So my function, evaluated with an input of 2.5, will give me an output of 6. Okay, on to the next example. This time we're going to use our floor. And we're putting in this -1 point blah, 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 1, right? So negative 1 point blah, 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 blah. 1 plus 3 minus 1. Okay, well, negative 1 point blah, 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 1 plus 3 will give me a positive 1.999999, right? 1.999 minus 1. Well, 1.99999 rounded down, it rounds down to 1. So this is going to give me 1 minus 1, or in other words, 0. Okay, moving on. This time we are not given an input, right? This time we're given an output. We're saying, when will my function have an output of 3? And we're dealing with our ceiling function on this one. So when will that function equal 3? Okay. So we would go ahead and divide by 2, and that would give me 1.5. And, oh, again, this is a situation where alarm bells should go off. I'm taking I have my step function isolated, right? And I'm taking something out of this. Well, the only thing when I evaluate that, the only thing that can come out is a whole number, not 1.5. So, this is a no solution. No x value that I put in there can give me an output that is 1.5. All right, moving on, we're going back to our floor function over here, and we're asking, when will it equal 4? Okay. So go ahead and add 1. Okay. There being a step function, there's a range of values that are going to work here. So if I subtract 3, I know that one of the edges, right, will be 2. So my cutoff, right, will be 2. Now, what happens, is this a right or a left edge of my step, right? So what happens if I go just above 2? If I go just above 2 to like 2.1, right, I'd have 5.1. And then rounding down, hey, 2.1 will still work. And if I do 2.2 and 2.3 and 2.4 and 2.5 and so on, those are all going to work until I hit 3. Once I hit 3, now this is no longer going to evaluate to 5. Okay, so my 2 here is a left boundary. So my answer is, it starts at 2, okay, and it'll go to 3, but 3 is not included because once I hit 3, I now jump to the next step. Okay, moving on, our next problem type is piecewise. I really don't like how this printed. Hopefully on your document, on your PDF form of the document, it's cleaner written than that. It should look like this. Negative 2 to the x when x is less than negative 4. Negative absolute value of x when x is between negative 4 and 0, including both boundaries. And a quadratic 4 minus x squared when x is greater than 0. So it should look, right, it should be written like this, would be easier. All right, so we're going to evaluate the piecewise function with an input of 0. So with an input of 0, the appropriate function to use would be this middle function, right? Because that's x is less than or equal to 0. So it's the middle function. So it's negative absolute value of 0. Well, that's just 0. Okay, next we're going to evaluate the function for an input of 2. Okay, the input of 2 would apply over here, right? Because 2 is greater than 0. So we're going to use this part of the function for an input of 2. 4 minus 2 squared. Hey, that's also 0. Okay, and then the last problem on this page, we have now an output of 5. So we have an output of 5. This one's tricky because, well, which function should I work with? And the answer is I could, in theory, have 3 places where I have an output of 5, right? I have to check all 3 of these. So when is negative 2 to the x going to give me an output of 5? Well, the lowest thing I can get here would, again, be 0, right? Because there's a negative in front. This is evaluated like this, right? Order of operations. So, and it really can't equal 0, right? It approaches 0. So this can never happen. So I know that that right there isn't going to work. I guess I shouldn't write x. I'll just say none. Okay, moving on to my next piece of my piecewise. Okay, when will that equal 5? Okay, well, again, this is an absolute value. So the lowest thing I can get here would be 0. And that can't ever equal a positive 5, right? Because as this x gets larger, and then you pick the negative up after, right? All values coming out of this will be between negative infinity and 0. So not going to work. Okay, moving on to the last piece of the piecewise. When will that equal 5? Okay, well, let's go ahead and solve. Again, we have a bit of an issue here, right? The lowest thing I can ever get out of x squared would be 0. And then I put a negative in front, so it's not going to work. You're going to have x squared equals negative 1. There's no real value here. Okay, I guess you do have complex roots to that, but no real value. So on a graph, this piecewise graph, we'll never have an output or a y-coordinate of 5. All right, so that's page 1. I'm going to stop the video here. It's getting pretty long, and then I'm going to upload a separate video for the next page.